We are going to talk about the center of mass of an object. That's our plan for today. The motion of rotating objects can be pretty complicated. If you toss a bat in the air while it's rotating, it looks like pretty complicated motion, but there's usually one special point in the object for which the motion is simple. In this example here, the motion of this point here is just a simple parabola, which is what we saw for regular projectile motion. But the motion of the bat, if you look at the outside of the bat, it's different. It's very weird. But this little point here is the center of mass of the bat. Included in the notes for this video is also some video examples of objects being thrown with their centers of mass indicated. So the center of mass traces out a parabola just like a ball, and the other points all rotate around it. The center of mass of a system of particles, that's going to be a first version of center of mass. So the center of mass of a system of particles is the point that moves as though all of the system's mass were concentrated there. So it's like if I have a bunch of different particles, or if I, in this example here, if I just have two particles separated by a distance d, then the center of mass of those two particles is given as x center of mass is equal to the mass of the second one over the sum of the two masses times d. That's if one of them is at the origin. But in general, the arbitrary way of calculating the center of mass is x center of mass is m1x1 plus m2x2 over the sum of their masses. So let me do an example here to sort of show you what I mean by all that. So here, in this example here, we have two identical masses. They're each 2 kilograms. One's at x equals 1 meter and one's at x equals 7 meters. So we can say, they're equal masses. What's going to be the center of mass? Well, we can predict that the center of mass will be halfway between them, right? They would both behave as if they were located, if it was a mass of 4 kilograms located there. Let's calculate it just to make sure that this is the center of mass. Okay, so let's calculate using the equation that was given. So x center of mass is equal to mass 1 x1 plus mass 2 x2 over the sum of mass 1 plus mass 2. So mass 1 is 2 kilograms, x1 is 1, it's located at x equals 1 meter, plus 2 kilograms times x2, which is 7 meters, and divided over the sum of those two masses, and it's 2 kilograms plus 2 kilograms, so that's going to be 4 kilograms. And you'll notice here, real quick, that the kilograms cancel out, and we're just going to be left with meters. But when we plug in everything, we end up with, we have 2 times 1 plus 2 times 7, so on the top we have 2 plus 14, so 16 meters divided by 4. And so 16 divided by 4 is 4 meters. And that is the location here, that is 4 meters. Right, so that's the center of mass for that one. Now, if I were to look at the second example I gave, so this example here, it's similar to the first one, except this mass is still 2 kilograms. Now this one is lighter. Now if they were both the same mass, then the center of mass would be located right in the middle between them. But where do you think the center of mass is going to be in this case? This one's heavier than this one, so the center of mass will be closer to the heavier one. We expect it to be over here somewhere. So let's calculate, that's going to be somewhere over here. It's going to be closer. We don't know exactly where yet, but let's figure it out. So x center of mass. So for this one here, we can calculate the center of mass, right? It's going to be m1 times x1. So m1 is 2 kilograms, x1 is 1 meter, plus m2 x2. So m1 is 1 kilogram, x2 is 7 meters, divided by the sum of the two masses. So it's going to be 2 kilograms plus 1 kilogram, right? And you notice that the kilograms cancel out everywhere again, so we're going to be left with just meters. So on top we have 2 plus 7, so we're going to have 9 meters, divided by 2 plus 1 on the bottom, 3. So our final answer will be 3 meters. So our center of mass here will be right there. So the center of mass of these two things is closer to the heavier one, which is basically what we expect. So here's another look at it. An example, sort of, here's a small mass and a large mass separated by a distance d. the center of mass will be closer to the heavier of the two particles. And this is the same two masses, but slightly further away from the origin. And the center of mass is going to be located there, just like the example we calculated. If there's more particles, we can generalize this equation to where we have, n particles. So if I have n particles, m1, m2, all the way to m sub little n, then I can find the center of mass for the whole thing. And we're going to call capital M the sum of the mass of all these particles, and then the center of mass is just going to be the product of mass times position for all of them divided by the total mass. Or another way to write it is 1 over m times the sum from I equals 1 to n for m sub I, x sub I. And we could even generalize this to 3 dimensions, right? If I have objects spread out in 3 dimensions, this will be the position and center of mass for those objects in the x component, the y component, and the z component. So if I want to do an example of that, it's not too difficult. Here is 3 particles, m1, m2, and m3, that are located at those locations, that are located as shown. So let me draw them on this grid here. So m1 is 1 kilogram, and it's at x equals -2 and y equals -5. So here, this would be m1, and that one is only 1 kilogram. Now m2 is at x equals +4 and y equals +4. So 1, 2, 3, 4, 1, 2, 3, 4. So here is m2. I drew it larger because it's a little bit bigger. And then m3 would be located at x equals 3 meter, y equals 0. Oh, so that would be somewhere maybe around here, and that's the biggest of the 3. There's m3. So the center of mass is going to be somewhere between these 3. It's going to be somewhere around here. I'm guessing, we're not exactly sure yet, but there's 3 objects, and we can use our equations to calculate the center of mass for these 3 things. So let's try it out. So here we're going to calculate the x1 first, and then we'll calculate the y1. So the x center of mass is going to be equal to 1 over m times the sum over all the masses times all the x values, right? From I equals 1, in this case from I equals 1 to 3. So the sum of all the masses, let's just calculate that for fun over here. So the sum of the masses will be m1 plus m2 plus m3. So 1 kilogram plus 2 kilograms plus 3 kilograms, so we have 6 kilograms is our total. So this will be 1 over 6 kilograms. And then it'll be the product of all those values. So it'll be 1 kilogram times the x1 is -2 meters. I'm going to skip sig figs for now to save ourselves a little trouble here. Plus, and then 2 kilograms times the x location for the second object, which is at 4 meters, plus 3 kilograms times the location of the third object, which is at 3 meters. So that ends up being 1 over, I'm just going to write 6 kilograms times, looks like 1 times -2 is -2 plus 8, so that's 6 plus 9, so that is 15. Like so. And when you plug in and calculate, you end up with 2.5 meters. You'll notice that the kilograms go away here. And when you do a similar calculation for y center of mass, right, it'll be 1 over 6 kilograms, and then it'll be m1, y1, so it'll be 1 kilogram times y1, which is -5 meters, plus 2 kilograms times 4 meters, plus 3 kilograms, and the y in this case is 0, right? So that term is going to go away. When you calculate that, you end up with 0.5 meters. So our y center of mass is at 0.5 meters, and our x center of mass is at 2.5 meters. So there's our center of mass. So let's draw it here on the graph just to get an idea where it is. So y is up a half and 2.5. So it looks like center of mass here, right? That's 2.5 for x, and that's 0.5 for y. So that's our approximate location of the center of mass for those three objects. It's close to the biggest one, which is about halfway between them, so that's not too surprising. Here's an interesting example from the textbook that I'd like to try. We have three uniform rods, each length 22 centimeters. The two vertical ones are each 14 grams, and the horizontal one is 42 grams. So I've labeled their masses M1 and M2. And we can assume for each of these cases that the center of mass for each rod, because it's uniform, is at the middle of the rod. So the center of mass for the top rod will be at x equals L over 2 and y equals 0. That's assuming that the origin is right here, the yellow dot. And the center of mass for the left rod here will be at x equals 0 and y equals minus L over 2. And the center of mass for the rod on the far right will be at x equals, it's a distance L over to the right, and y equals minus L over 2. So let's call this one rod 1. Let's call that one rod 2. We'll call this one rod 3. And they each have their own masses too, right? M3 I'll use is 42 kilograms, and M1 is 14 not kilograms, grams, and M2 is also 14 grams. So we're going to ignore this one here, and this is grams, not kilograms. So we can say, well, we have the center of the mass of each individual one, so we can calculate the center of mass of the whole. So the center of mass of the whole, right, will be, for x, will be M1 x1 plus M2 x2 plus M3 x3 over the sum of M1 plus M2 plus M3. And if we were to, well, let's plug in everything for fun here. So on the top, it's going to be, let's see, M1 is 14 grams, X1 is 0, plus M2 is 14 grams, and X2 is L. We'll leave it as L for now. Actually, no, we can put in for L. It's 22 centimeters. Let's make a note of that, 22 centimeters. And then the third one, it's 42 grams times X for the third one, which is L over 2. So it's going to be at 11 centimeters. And that's going to be divided by the sum of all three of those masses, right? 14 grams plus 14 grams plus 42 grams. And that turns out to be 11 centimeters, which is basically what we expected. We expect it to be, we expect it to be along here. And now we can do it for y as well. So for y, center of mass, right, it would be M1 y1 plus M2 y2 plus M3 y3 all over the sum of all those masses, M1 plus M2 plus M3. And if you were to calculate it all, you would get, let me see, you would get minus 4.4. So our center of mass will be somewhere here, approximately. So even more general than this, if I wanted to, well, let's go to a more general situation. If I want to find the r vector or the position vector for the center of mass, I can write it like this, right? 1 over the mass of all the particles times the sum of each individual mass times each individual position vector. So that's just combining x, y, and z into one vector. Now, for solid bodies, like if I have a sphere or a cube or something, you can take the limit. As these particles get small, you can integrate over the whole volume of a solid and calculate the center of mass for a solid. So in the limit, x center of mass is 1 over the mass of the object times the integral of x over all the mass over each little dm, each little infinitesimally small piece of mass. Same for y center of mass, same for x center of mass. So this is a pretty general way. I would show you one example real quick. So we limit ourselves to objects of uniform density. So if it's uniform density, remember density is mass per volume, or if I want to do it infinitesimally, dm over dv. So I can substitute for the dm in terms of dv, and I end up with x center of mass is 1 over the volume times the integral of x over the entire volume. And there's usually lots of ways that you can get around this, but I thought I would do one example real quick. Let's say I have a solid block here. So this is a solid rectangular block and it has a mass m. And I want to find its center of mass. Well, we know where its center of mass is going to be, right? It's going to be, you know, if I were to draw the axis behind here, it'll be at about a over 2, about c over 2, and about b over 2. So you know that it'll be somewhere like in the middle. It's hard to draw here, but it'll be in the middle of this thing here. At x equals a over 2, y equals b over 2, and z equals c over 2. So we can find the location by doing the integral. And I'm just going to do one of them real quick just to give you, because the other two will be the same. But if I wanted to calculate the center of mass for x, it would be the integral, 1 over the volume, times the integral of x dv. So 1 over the volume, and the integral dv is really just 3 integrals. It's the integral over a volume is just the integral with respect to x times the integral and the integral with respect to y and the integral with respect to z. I won't ask you to do this on your own. I'm just showing you this because it's cool. The integral from x is going to go from 0 to a, because in the x direction the box goes from the origin to a. The integral over y goes from 0 to b, and the integral over z goes from 0 to c. So let me collect this out. So 1 over v is, let's see, I'm going to collect all the x1, so it's the integral of x dx from 0 to a. I'm going to collect the y integral, and there's no y value, so it's just the integral of y from 0 to b, and then the z integral is the integral dz from 0 to c. So if I have 1 over v, the integral of x from 0 to a, that's an easy one. You just end up with a squared over 2. The integral of basically 1 from 0 to b with respect to y just gives you b, and the integral of nothing with respect to c just gives you a c. So let me rewrite this now. I'm going to factor out one of the a's, so a, b, c, and then the other a is going to be over here. And notice that a, b, c, width times height times length, is just the volume, right? So that means that this becomes 1 over the volume times a over 2. So that's equal to, you see the volumes cancel out, and that's equal to a over 2. So the center of mass for the x component is a over 2. And you would get the same for the y center of mass. You would get that it's b over 2. And for the z center of mass, you would get that it's c over 2, right? So it is exactly where you expect it to be. It's right in the middle of the block at at x equals a over 2, y equals b over 2, and z equals c over 2. So it's going to be right in the middle of the whole thing. That's just for interest's sake. And it turns out that the motion of a center of mass still follows Newton's second law. So if I have the center of mass of an object or a bunch of particles, then the center of mass of that collection still follows Newton's laws. And it still follows Newton's second law. So F net is the net force of all external forces acting on the system. So those are forces from outside. If there's any forces between the particles inside the system, they don't affect it. It's only external forces. And capital M is the total mass of the system, and acceleration, COM, is the acceleration of the center mass of the system. So an example here is if I launch a firecracker and then it explodes here, it's following a parabola and then explodes here, all the individual pieces, if you calculate the center of mass of those individual pieces, they will still have the same trajectory as it had before it exploded until they hit the ground. That is, of course, ignoring air resistance. And same with the ballerina here. When they jump up in the air and their arms and legs flail around, even though different pieces are moving around, the path of her head is kept constant just by stretching in the right ways, but the center of mass still follows a parabola. And just to drive that point home, I was going to do an example from the textbook here to sort of show you how that works. So let's say I have 3 particles, 4 kilogram, 8 kilogram, and another 4 kilogram particle, and they feel the 3 forces here, F1, F2, and F3. Well, I can find the acceleration of the center of mass by using this Newton's second law for the center of mass. So the acceleration for the center of mass, right, will just be the net force divided by the mass. And these 3 forces are 3 external forces acting on the object. So I can treat the F net as the sum of these 3 forces. So in other words, F net is going to be basically the sum of those 3 forces, F1 plus F2 plus F3. So I can calculate the acceleration. So this is going to be F1 plus F2 plus F3 over the mass of the whole thing. And we can calculate the mass of the whole thing, right? The mass is going to be the sum of the 3 masses, and you look like there's 2 4 kilograms and then 8 kilograms. So the total mass is 16.0 kilograms. And when you plug all those numbers into here, you end up with a total acceleration of 1.03 meters per second squared in the I hat direction plus 0.530 meters per second squared in the j hat direction. So that is your net acceleration for this thing when you plug everything in. So here's a simulation. It's a PhET simulation, P-H-E-T, from University of Colorado, where you can see the motion of multiple objects. And right now we have, a mass. I'm going to make mass 2 be a 1. So the object 2 has twice the mass of object 1, and they're moving towards each other. So if object 2 has twice the mass, where do we expect the center of mass to be? Well, let's turn it on. It is closer to mass 2. Now when I hit play, look at this. The center of mass of the whole thing, even after they collide, keeps moving in the same direction. So let me back it up a little bit here. If I restart it here, when I hit play, notice that the center of mass, even after they collide, doesn't move, doesn't change. It just keeps going in the same direction. Now, as long as they're interacting with each other, the center of mass of the 2 objects stays the same. As they get further and further apart, you see the center of mass is still something between the 2 of them. Once they hit a wall, though, the center of mass can change its motion. So watch, when one hits the wall, the center of mass's motion changes. But the center of mass is always going to be something between the 2 of them, and it changes whenever they hit a wall, which is an external force. Okay, now if I were to add some extra balls here, you can see the center of mass of the whole thing. So let's put, all 4 balls sort of close-ish to each other and moving slowly away from each other. So let's see here, the center of mass is going to be somewhere between here, something like this. I'm going to make them go real slow. So when I hit play, the center of mass will move slowly, and it keeps moving until one of them hits an external wall. Then the center of mass changes its motion.